Hey, it's Tony from Adafruit, and in this video I want to look at a brand new and exciting thing with MicroPython. So we're going to look at a port of MicroPython to a new processor architecture, something we've been working on for about the last month, and we've got some good progress, and so it's still early days. It's a beta release, everything's not finished, but really cool things that you can do with MicroPython on different boards. So in the past you might have used something like this guy, and apologies, I'm getting over a cold, unfortunately, so I might sound a little bit differently. But this is the ESP8266, the Feather version of it. Let's see if we can focus. There we go. So real common little Wi-Fi microcontroller, runs MicroPython really well. But you might have wondered, okay, well, I want to run MicroPython on a different board, maybe something like an Arduino, so maybe like the Arduino Uno, for example. And unfortunately, the Uno, it uses an AVR processor, which is just a little too slow, not enough memory and resources to run something like MicroPython, because remember, MicroPython is interpreted, there's a little bit of overhead in how it works, but you get a lot of benefits because of that, so you can do things like interactive REPLs and running Python code at a terminal. But we looked at some different chips, and one of the chips that's really cool is something that's used in this thing. So this is the Arduino Zero. This is the M0 Pro. It's kind of the Arduino.cc version, which I guess nowadays .cc.org, that dispute is finally done. So, but the Arduino Zero is kind of the version of this you can get today. And it uses the chip, the Atmel SAMD21, which is a Cortex M0 Plus. A lot of fancy words, but basically that means it's a 32-bit microcontroller, similar to what you might find in more high-end interesting electronics, like maybe a smartwatch might have a Cortex processor, maybe a real fancy version. Some of the other MicroPython boards, like the Pi board, has a Cortex processor. It uses a fancier one that's faster and has more memory and more capabilities. The SAMD21 is kind of nice in that it's a balance of cost and performance. So it's not too much more expensive than the AVR type boards, but it gives you the ability to use MicroPython because it has more memory, more processing power. So it has 32 kilobytes of memory of RAM. It has 256 kilobytes of flash memory, so that's about like, I think 8 times more than an AVR. So quite a bit more space on it, and it can do lots of cool things. It can actually act like a USB device, so you can make it look like a USB storage device. And so that's why we wanted to look at supporting MicroPython on this chip, because it's used in all kinds of fun stuff like, let's see, I don't think I have one handy here, but I'll show you in a moment here. The Feather M0 board is a whole line of boards that we have that use this AT-SAMD21 processor. There's also the Arduino Zero, like I mentioned, and probably more boards that are coming in the future that will use this processor. And so it'll be an interesting platform to explore MicroPython, because this could be the platform that helps you use MicroPython on boards that are much more similar to Arduino type boards and have similar amount of I/O and capabilities as those boards. So let's just kind of dive in. Like I said, I'm going to explore a brand new port of MicroPython in this video. It's still in development, it's still beta, there are going to be bugs and issues and things, but we're just kind of getting it out there to hopefully get some feedback and get maybe some advanced users to starting to play with this and see how it works. So let's go to the main view real quick. And let's see, we'll go to desktop view here for this. Okay, cool. And yeah, folks are asking questions in the channel, so yeah, feel free to ask questions, and I'll try to get to them. Usually at the end is when I can get to questions. But anyway, so I'm looking at a guide, and this is in the learning system right now. We'll publish probably a blog post tomorrow on this, but this is a guide on MicroPython for the SAMD21. And so you'll want to check this out. This kind of talks about how to load pre-built firmware that we've made for it. So we've compiled firmware ahead of time so you don't have to compile it. And you can load this on either a Feather M0 or an Arduino Zero, so we have 2 different firmwares for it. It tells you how to build the firmware because, like I said, this is in development, it's a little bit experimental, so if you want to get your hands dirty and start playing with the internals of MicroPython, maybe start extending it, adding more support, things like that, hopefully you can learn how to build it. We've set up a little Vagrant VM. I did a previous video on this using a virtual machine, so that'll give you a lot of good info. Then I have a quick start guide that just runs through like what are the features, how to use basic things. So we have the basic hardware support enabled right now, so like digital I/O, analog I/O, I2C access, NeoPixels. So we'll go through some of that and what you can do with that. And then a few of the cool features like the USB mass storage that I mentioned. So this can actually look like a USB USB drive when you plug it into your computer. And remember, MicroPython has a file system, so you can copy files to that file system really easily. Like, you don't necessarily have to use tools like AMPI that I've shown before that use the serial connection. You can actually just connect to your computer, start copying over source code and interacting with it that way. And then also this concept of frozen modules that we'll see if I have time for this. This might be a separate video for that. So let's just kind of dive in. Like I said, this is the guide, and I'll put a link in the description when this goes up on YouTube, so you can find that link and find this guide. And you'll definitely want to read through this and see. And like I said, this is, not for total beginners yet. We're still in development. We're still working through issues. Not everything is supported by MicroPython yet, but hopefully enough stuff to maybe kick the tires and start building some interesting stuff with this. So this talks a little bit about, what is the port. I think I've already gone through that. So let's just dive in. And as an example, so in the upper right here, I have, this is a Feather M0. So this is basically like the simplest AT SAMD21 processor board you can get right now. It just has the chip on here and then some space for prototyping, all in the Feather form factor. So real nice and easy to get started with. So that's right here. And then I have a whole bunch of accessories that we'll play with in this video. So I'll just kind of demonstrate how to deal with like NeoPixels right here. Here's a potentiometer for analog input. There's a button. There's an LED that we'll mess with. And then this is a little I2C sensor right here. This is a temperature sensor, the MCP9808. So okay, first things first. If you have an M0, and also like this does work with the Arduino Zero, so this thing here, I won't show it in this video, but the Feather M0 is what we're using. If you have one of those, you have to load the MicroPython firmware onto it first. And before you do that, you want to go through and follow any guide to get started. Like with the Feather M0, there's a guide that shows you how to set up the Arduino IDE so you can program it with sketches from Arduino. And make sure you go through that, because like on Windows, you usually need to install a driver. So you'll have to have that installed to get all of this kind of bootstrapping or this setup in place. And then, like I said, you'll have to load MicroPython onto it as a firmware, so that'll get rid of any Arduino sketch that you have that's on there. It doesn't mean that you can never use that board with Arduino again. It's actually really easy. You can just load it back into Arduino and flash it with a new sketch, and MicroPython will be gone. Everything will be back to normal for it. So you can switch between both. If you want to play with MicroPython, and then if you realize, maybe you want to go back to Arduino, it's really easy. You just use the Arduino IDE, and I mentioned the guide how to do that. So, just a warning, like it'll get rid of whatever's on your board, but it's easy to go back to using it with Arduino. So there are two things you need to do. The first thing is you want to look on GitHub. So on Adafruit's GitHub, that's where we have our MicroPython port right here. It's in our own kind of fork of it right now. We're still developing it and kind of figuring out how we're going to go with it. But this is where the code is. So, and one note, like, don't go to the upstream MicroPython repository yet. This isn't in there. Don't open issues against that yet. Everything is just on Adafruit's GitHub repository right now. So just a word of warning that it's all in here. But you'll need to download it, and you want to go to the releases page. So I have this up here, and just look to see what is the current release. I didn't want to link to the current release because it's probably going to fall out of date as we add new releases. But right now, you can see it's 1.8.4, 2016, 10.14. We're still thinking what we want to do with the version numbers, but we're kind of matching the upstream MicroPython version right now, the 1.8.4 release here. And you can see there are a couple things here. There are these .bin files. There's one for the Zero and one for the Feather M0 Basic. And this Feather M0 Basic one, this works with any of the Feather M0 boards. So I mentioned in the guide we have the Wi-Fi board with the AT-Wink 1500 Wi-Fi radio. We have the Bluefruit LE board with the NRF51. We have all the radio boards like the 400 and 800 megahertz packet radios, the LoRa board, there's the Adalogger board. So all kinds of M0 Feather boards out there. This firmware will work with all of them, but just note, like for the Wi-Fi board, the Bluefruit board, none of those have implementation or support for the Wi-Fi radio or the Bluefruit Bluetooth radio yet. So, you won't get those features. You can still do the basic digital analog I/O, but right now none of that stuff's implemented. But hopefully in the future, because that could be pretty cool to do, like Bluetooth Low Energy with Python and MicroPython, cool stuff there, even like long-range LoRa radio stuff. There'll be some neat stuff in the future to keep an eye on. But anyways, so that's basically what these two firmwares are. And then if you do have the Arduino M0 Pro, which is the one that I actually have here, the .cc version, read the guide, because there are a few little weird things you have to do with that board. You actually have to flash it as an Arduino Zero, not the M0 Pro, but an Arduino 0, which is the .org version. Basically, that just lets you use this BOSSA tool. That's how you load firmware. I mentioned this in the guide, so read the guide if you have that board, because there's a little bit of an extra step for you to deal with. But the first thing is I need to download the firmware. So I'm going to flash this board right here. So I'm going to download the Feather M0 basic firmware. And I'm just going to do this in a directory right here on my machine. So I'm using a Mac, but this should work on any system. Download the firmware, put it somewhere. I'll use wget, which just goes and grabs the file. So, okay, so I've got this firmware.bin file. Now to load it onto the board, I have to use something else. I can't just natively do this yet. I can't like drag and drop it. I have to use this tool called BOSSA, and a very specific version of BOSSA. So I mentioned in the guide, you'll want to go to its GitHub release page, and you want to make sure you get version 1.7.0 or higher. If you get an older version, because if you actually search on Google, you can find the home page for BOSSA, but the download there gives you an older version that doesn't support this processor. So follow the guide, and you really do have to use this version of it. They distribute some binaries here of the BOSSA C, which is just like a command line compiler tool, which is what we'll use here. But you do want to download one of these for your platform. For Mac, you want the Apple Darwin version. For Windows, you want the MinGW32 version. And then for Linux, there's an ARM version, so like Raspberry Pi. That's kind of cool. There's also the i686. So this would be, I'm assuming 32-bit. I haven't really checked that. And then there's an x86-64. This is probably the one you want on Linux. And then like worst case, it's actually really easy to compile this. If you're on Linux or Mac, you can download the source, and it's just a configure, make, install kind of thing. So, on Windows is really where you probably have to download this. So you want the MinGW32 version, which should run on 64-bit Windows also. So get the version of this. So for on Mac, I'm going to copy the link to this, and I'll just download it into the same directory. And if you're on Windows and you get these .tar.gz files and you wonder how the heck do I deal with this thing, look at a tool called 7-zip. I linked to it in the guide. 7-zip's a nice little tool. You can use this, it's open source, and it should be able to open these files, because unfortunately on Windows you usually don't have these tar and gzip tools installed. Okay, so I downloaded it, and then I just want to open it up. So tar xvfz, this basically unzips a tar gz file, and so I pointed at the file, and so this opens it up, and now I have a directory here, this BOSSA C 1.7.0. So if I go in there, there's just this BOSSA C command. And if I run this, and this is pretty good, make sure you can do this, run it with the -- help command. This will just show, okay, here are all the options for this tool. So just make sure that you can run the tool. Make sure you don't get some crazy error or that it can't find it. Just give it a quick shot to make sure everything's working before you try to flash the board. So you can see it has a ton of options, but it's actually pretty easy to use this. So from within this BOSSA C directory, what I'm going to do is I'm going to flash the MicroPython firmware onto this chip. So remember, I downloaded that MicroPython firmware. It's in the directory one level above me, but I can reference it in a second here. Okay, so before I flash this board, for the Feather M0 board, basically what you need to do, there's the reset button, and you want to double press it. So if I double press it, notice that this red light is now kind of pulsing on and off slowly. So that means the bootloader is running, and this BOSSA C tool can now connect to the chip and actually reprogram it or send it new firmware. And you can actually double check. So if I list all the serial ports, I should see, so yeah, on Mac, the serial port for this is going to be this USB modem device. It's a USB CDC device, but you do want to make sure that, when this bootloader is running, that you can see there's a serial port. On Windows, you would see a COM port, like COM4, COM5, something like that. If you don't see that, then you probably didn't install the driver. So go back to the guide for using that Feather board and make sure that you get the driver installed for that. Okay, so I see that serial port, and then what I want to do to program the firmware for this is I'm going to use that BOSSA C command, and so because that command is in the same directory, I have to prefix it with this // to just tell, in a Unix system, if the tool isn't in your path, then you need to tell it, I'm running it from this directory in here. And I mentioned this in the guide, so just be aware that it's, you might need to change how you run this. And on Linux, you probably have to run with sudo unless you somehow have access to the USB modem device as your normal user. So, if it fails with it can't find the device, try with sudo, it'll probably work. for that. Okay, so the bossc command, there are just a few parameters we pass in. We want to do -E. This is going to erase all of the memory on the chip. And just fair warning, if you had like MicroPython loaded on here before and you had files in the file system, you're going to lose them all because this is going to erase everything. So just make sure you back things up before you load up the new firmware. Okay, the erase option, then the write option, because we're writing new firmware. We want to do the -V option to verify. So after it writes the firmware, it'll check that it actually wrote exactly those bits out to the board. The -R option, this will reset the chip so that you can connect to the serial port and see the Python REPL without having to reset the chip manually. And then the P option, this gives the port or the serial port that the board is connected to, and that's the port that I just saw right here above, this TTY.USB modem. Excuse me. Now, the weird thing about this bossc tool, it doesn't actually take the full path. It just takes everything after /dev, at least on Linux and Mac systems. So, I don't know, for whatever reason, just grab everything after the /dev, and that's what you want. On Linux, you're going to see probably a TTY ACM0 is usually the device, so that's what you want. And on Windows, it should just be your COM port, like COM4, COM1, something like that. Look in Device Manager if you aren't sure where to find the COM port for your device. Okay, so the -P option, and then the last thing is I need to give the firmware.bin file that I want to write to the chip. And so that's one level above my current directory because I'm inside this bossc directory. So I just want to load up the Adafruit, MicroPython, FeatherM0 Basic, firmware.bin file. So do that, and then I'll hit enter, and we give it a second here. And let's see what just happened here. Something is wrong. Okay, let me reset the bootloader here. So this is, hey, it's live internet. So let's see. This was just working a second ago. So we'll see what happens. I might have gotten something wrong with the name of the device, but let's try this again. So we'll see. Okay, there we go. I don't know why. For some reason, the bootloader, maybe it ran too long and it timed out or something. So you should see something like this. And if it goes wrong, try resetting it like I just did and give it another shot. If you get an error that it can't find the device and you're on Linux, try running with sudo. That might be an issue for you. But this is what you should see. So it erased the flash memory. It wrote out all the bytes of the firmware. It verified that it wrote all those bytes exactly as it expected, because sometimes there can be errors in that, and then it reset the board. So the MicroPython firmware should be loaded now on this chip. So let's try it out. We'll use the screen tool to access the serial REPL. But go back, I mentioned in the guide, if you're on Windows, you have to use PuTTY or a tool that lets you access the serial port. I've mentioned this in a few different guides, so I've got good links to info on that. So we use the screen tool, and then we should see there's this USB modem device, and on Linux it'll be a TTY ACM device. On Windows it'll be a COM port again. And then 115200 baud is the baud that I want to use to connect to this. And hey, look at this, we've got a Python REPL. So I can say, hello world, for example. And remember, this is running on this little FeatherM0 chip right here. So this is pretty cool. We've got MicroPython going on here. And this has all the same core Python language features. So, things like printing and functions and classes, and even like the functional style of like, you want map and filter and all these fancy things. All of that stuff's supported. Some of the modules aren't supported yet. So, MicroPython has a ton of modules, especially in the ESP port. So things like JSON parsing and stuff like that. So not all of that is there yet, but I'll run through in a little bit what we do have. And then we also have some modules for like basic hardware access that we'll go through here in just a second. And maybe too, before I get into it too far, it's also maybe good to point out just, what are the specs and the capabilities. So this SAMD21 processor, this has 32 kilobytes of memory, and some of that memory is going to be used up by MicroPython. I actually haven't looked to see how much is available right now, but somewhere around like 16K-ish is probably available to you. So a decent amount of memory, but this isn't going to set the world on fire. You're not. It's certainly not a Raspberry Pi. You don't have megabytes of memory on here. It has 256 kilobytes of flash memory, and we reserve 64 kilobytes of that for the file system on the board. So 64K of space basically for any of your Python source code or data files that you want to store, things like that. So again, a decent amount, like an Arduino Uno has 32 kilobytes total for storing your source code and things. So, a little bit more than that. But again, this is Python code, so it might be a little bit larger. So that's kind of interesting, but look in the future. We might have boards that maybe have more memory and things in the future to look at. And then the processor runs at 48 megahertz. So it's faster than an Arduino Uno, but again, because you're running interpreted code, there's just some overhead in general. You're never going to be as fast as that native code that's running exactly on the processor. But hey, if you want that speed, you can extend MicroPython, implement C functions and things for that. But anyways, just wanted to say those are kind of the capabilities. So, this isn't going to be like a barnstormer. This isn't going to be the fastest chip in the world. But again, it's, not super expensive, and it's real simple and small and easy to get started with. And so having that option to run MicroPython is going to be really cool on this board. Okay, so that's all there is to loading MicroPython is, download the firmware, use that boss.c tool, and load the firmware, and you're good to go. At this point, you've got the Python REPL, and you're ready to start exploring how this thing works. In the guide, I do mention how to build the firmware, and there's actually a whole video that we did when we were out at the Adafruit factory. Did it with Scott, who's kind of the brains behind all of this MicroPython stuff. So hats off to Scott, who's done this port, pretty much all the work for it, and it works really well. But anyways, we did this little video where we showed there's a Vagrant-based virtual machine you can use to build the firmware. So that firmware.bin file that I downloaded earlier, this thing, all the source code is up on GitHub. This is an open source project. So you can go and you can build it yourself. And there's some advantages for that. Like if you want to add new capabilities, you're going to want to build it yourself. If you want to bake in modules for better performance, you need to be able to build it yourself. So we'll look more at this maybe in a future video, or at least look at this guide page if you're curious. But you don't have to build it yourself if you just want to get started. Like I showed, you can download the firmware bin file, load it up, and you're ready to go for it. But when you do want to go further, check this out for how to build it yourself. And then this quick start guide. So I'll kind of dive into this now. So like I mentioned on this guide, this is all in development. There are going to be bugs and little issues and things. Not all of the MicroPython features are supported. We might be changing some of the interfaces slightly for MicroPython stuff just to help us support all the different boards and things that we want to do. So, be aware there's some differences here, but we'll kind of try and call this out. And in this quick start, I really just tried to go through, like, here are the major modules that we have implemented right now and examples of how to use them. So we'll just kind of dive in with the machine module, which is kind of the standard right now for how to access hardware in MicroPython. So we've got digital I/O and analog I/O supported with that. So let's try it out. We'll open up the machine module. Let's try this LED first. So I'm going to hook this LED up to one of the digital inputs on the board. So I'll pick, how about input number 5? Let's see, we'll plug this in. And the LED I just have wired up. So the cathode of it, or the longer leg of it, is going to, or sorry, the cathode. Boy, I'm mixing it up already. But basically, well, here I'll show you how I've wired up. So here's the longer leg. This is going to my digital input. The shorter leg is going through a resistor down to ground. So you want to hook it up that way because the current has to flow in a certain direction through the LED. Okay, so now that I have this imported, let's create an LED object, and we'll say LED equals machine.pin. This is just how you make a digital output in MicroPython. Now for our port, for the SAMD21 port, all of the pins are identified by a string. So in this case, D5, this is digital input number 5 on the side of the board, is what I want to use. In the guide, I mentioned exactly all the pins. So you can see down here, there's like A0 through A5 for all the analog inputs. We actually have names for the SPI pins, the I2C pins, all the digital pins that are on the board here. So it makes it a little bit easier to use this. So you don't have to do some mapping between module pin GPIO numbers or like board pin numbers. We're just going with the board names basically. So D5 is what I want. And then I want to make this an output. So machine.pin.out. And okay, so now if I say, let's do LED.high, then cool, turns it on. We're setting it to high level, and then LED.low, set it down to low level. So simple, a digital output basically. Turn it on and off. Easy to blink an LED with this. So that works. Let's do a digital input. So I have a push button over here. So this little guy is a push button. And I have it hooked up with one of the corners is going down to ground, and then the other corner is just connected to that D5 digital input. And so if I make my button a machine.pin D5, and now if I make this an input, and if I add a pull-up resistor, so then this means that normally this input is going to be tied to a high logic level. If nothing else is pulling this down to ground, then it's going to be at a high logic level, so it's not going to float down to random values. You know, I went through all this in the digital input, digital I/O MicroPython video, so check that out if you're kind of curious. But I'm going to make this the digital input with a pull-up resistor. Now, if I read the value of this button, so the button.value function, it's going to give me 1, which means a high logic level. And that's what I expect, because if the button is not pressed, then there's nothing connected to this input right now. So it could be floating at like high or low random values, but because of that internal pull-up resistor, it's always going to go back up to a high logic level. So I know when the button is not pressed, it's at a high logic level. If I press the button, then hey, check that out. It goes down to a 0 value like that. And if I release it, it goes back up to 1. So that's how you read a button like this. If you connect it to ground, there are other ways to read a button, but this is a pretty simple way to do it, is using a pull-up resistor like that. So cool, we've got digital outputs, digital inputs working. That's, you could do some basic stuff with that already. That's pretty cool to talk to, you could talk to like a PIR sensor that will detect motion. You could fire off a solenoid, you just need a digital output for that. So lots of cool possibilities with that. Okay, so that's digital I/O. Let's look at some of the analog I/O capabilities. So we have the analog to digital converter supported, pulse width modulation outputs, which are kind of like ways that you could fade an LED or kind of control the brightness of an LED. And we do even have support for the DAC, the digital to analog converter. And I won't really show it in this video, but it's kind of cool. It's actually one of the features that this SAMD21 chip has. Things like the AVR microprocessors used in the Arduino Uno, they don't have some of those peripherals like a digital to analog converter. So this is one of the cool advantages of using a chip like the SAMD21, is that you get more features like that. Okay, so let's start with the analog input. I'm going to hook this up to a potentiometer, and I'm going to connect it up to the A0 input on here. So the analog 0 input, make sure I get the right one. Yeah, there we go. And so this potentiometer, I just have this hooked up. One of the three outer, so there are three leads to the potentiometer. One of the outer leads I have connected to ground. The other lead I have connected to 3.3 volts power, and then the middle lead, the wiper, is kind of the output of it. And so I just have this connected to one of the analog inputs, the A0 input on the board. So this way it works as a voltage divider, and it'll change the voltage as I twist the potentiometer a little bit. And so we should see, so I'll make an ADC object, so machine.adc, and for this you have to pass in the pin that you're referencing. So this is the A0 pin that I'm using. You don't have to set it as like an input or an output or anything for this. And so I have this ADC object, and if I call adc.read, then I get a value like this. And so if I twist this down to like a lower level, I get a smaller value. I go all the way down and I get, pretty much a 0 value. If I twist it back up, I get, a higher value. Now the values that you'll get at most are 12-bit values. So a value between 0 and 4095 like this. So just, be aware, like every analog to digital converter has different capabilities and different precision. This one's kind of nice. It's a little bit nicer than an Arduino Uno. I think the Uno only has a 10-bit analog to digital converter. This one has a 12-bit, so you get a little bit more precision with that. But it's as easy as this, just using these functions here, creating an ADC object and then calling the read function on it. So that's pretty simple. And one little note too, I forget exactly what the analog reference is for it, but it looks like it's around like 1.6 volts or something like that. So again, this is all kind of in development and kind of beta stuff. So, we'll update these things as we go, but just be aware that, you might have to tweak the voltages that you're setting into this to fall within the range that the processor supports. Okay, let's try the PWM output next. So I'm going to hook the LED back up, and I'm going to hook it back up to, let's go back to digital pin 5. So we'll go back to this pin. So I hooked up the LED again, and let's make one of the PWM outputs. So we'll say LED PWM equals machine.pwm, and I have to pass in the pin that I'm using. So we'll say the D5 pin, and just to be sure, I'm going to make it an output again for this. Okay, so I have my PWM object. Now, one thing we don't support right now is changing the frequency of the PWM output. And if you aren't familiar with PWM, I did a whole video on MicroPython analog I/O where I kind of explain it more. It's you change a signal really quickly, like you turn something on and off really fast, and that can approximate kind of an analog signal that has different voltages. But one thing that you usually want to control there is the frequency, or how fast it changes that signal on and off. And right now it's just a fixed frequency. It's 732 hertz that we're using right now, so it's just kind of a basic first stab at it. Eventually we'll add support for setting different frequencies, but just be aware right now, it works for like controlling the brightness of an LED, but it might not work for like controlling a servo or something right now for this. But anyways, you can change the duty cycle, and so that's how you control the brightness. And the duty cycle is an 8-bit value on this chip, so a value from 0 to 255. So value 0 means it's totally off, and a value of 255 means that it's totally on. So you see the LED turns on. And if I go somewhere in between, like let's say 127, then notice the brightness kind of changes a little bit, and it might be hard to tell. I'll go back to 255, and it's a little hard to tell in the video. So maybe let's jump down to like, how about 64, something like that. So watch the LED, it should get much dimmer. So yeah, you can see it's still lit up, but it's noticeably dimmer in this case. So, we're changing how often that PWM signal is on versus off, and then that basically changes effectively the voltage that this LED sees, so that it's seen, it's turned on less often than it's turned off, and so you get a less bright LED in this case. So, and you can go back up to 255 for a max value here. So that's pretty cool. You've got PWM output, so you can control the brightness of an LED with this. That's pretty fun. Let's go back to the guide. And like I mentioned, we do have support for the digital to analog converter. I don't really have a good demo of it to show right here, but it's as easy as just creating this machine.dac object. Now it's fixed on the SAMD21. There's only one digital analog converter, and it's output on pin A0. So the A0 analog input is also the output of the digital to analog converter. So I show some basic examples here. Just like PWM, you have to pass in a value. In this case, it's a 10-bit value that you pass in. So a value from 0 to 1023. And then that will set the output voltage proportionally based on that. So like a value of 1023 will give you the full 3.3 volt output. Value 512 gives you kind of half of the analog reference voltage, or 1.6 volts. So just be aware, that's how the digital analog converter works. And this could be kind of cool. One thing that you might want to use for this would be like connecting it to a speaker and playing samples of music. But again, because this is an interpreted Python code, I'm not sure it'll be fast enough just in high-level Python to play music back. But that could be a good thing to implement in a C function, like a wave playback or something function that you could then call from Python, which would be kind of cool to play with later. So that's a cool thing to look at. Okay, so the last thing I wanted to look at with the hardware was, second last thing, there are two things. I2C access. So we do have access for talking to I2C devices. So I have this little MCP9808 sensor, which I did a whole guide on MicroPython I2C stuff where I looked at this sensor. So go back and check out that guide if you want more details. But I'm just going to hook this up to my board right here. So I'll unplug the LED, and I'm going to hook up the SCL, the clock line. So I'll hook SCL up to SCL. And then I'm going to hook up the SDA, the data line, to the data line on the chip. There we go. So that's all hooked up. And then it also has power and ground hooked up. You're going to need those, obviously. And then to use I2C, it's pretty similar to the other boards. And I'll show you, there is one little difference that we have. Again, you're using the machine module here. You want to make an I2C object, and this is similar to other boards. There is one difference in that we don't have a concept right now of the interface number. So there, on some of the boards you use like interface 0 or 1 or -1 sometimes. We kind of got rid of that for now just to simplify things. But you do need to specify which pins, which pin is the clock pin and which pin is the data pin. So first the clock pin, this is machine.pin SCL, because remember we've got these nice string numbers, or string names for the pins. So the SCL pin, and then the machine.pin SDA pin for the data line here. And one thing to note, this is a hardware SPI implementation, so it's actually the chip itself that's going to do all of the SPI transactions. This is in contrast to the ESP8266, which has a software SPI implementation. And with the ESP8266, you can actually use any two GPIO pins as your clock and data line because it's just going to bit bang the I2C protocol for you. You know, there are advantages and disadvantages. It's nice in that you can use any two pins, but it's really slow. And, you know, it works for most devices because I2C is a pretty slow protocol. But it's sometimes nice to have this hardware capability. So just be aware on the SAMD21, you know, you can only use certain pins that support the I2C interface. So in most cases, you really just want to use the SCL and SDA pins that are explicitly marked on the board. But if you look at the datasheet and if you see which other pins support the I2C clock and data lines for different SIRCOMs, so this is like a really advanced feature of the chip, then you can actually use different pins here. You know, it's going to use that hardware I2C interface. But to keep things simple, you probably just want the clock and the data lines here. So, okay, so I create this I2C object. Now at this point, you do have to do an initialization that kind of configures the chip to say, okay, we're ready to do this hardware I2C. So you want to call this init function first. And then once you do that, you can start calling all the different I2C commands to like read data from the chip, write things to the chip, for example. But you do have to do this init first. And you can also, after you do this, you can call the scan function, for example. So I showed in a different video, you know, this will look for all the devices that are connected to the I2C bus. I get a result back. So this is telling me there's a device with address 24 in decimal connected to the I2C bus. And that's good because that's the address of this MCP chip that I see here. So, you know, basically it's telling me that this SAMD21 is able to find and talk to this chip. So that's good. I2C is working. And then let's see, I'll show real quick, maybe I won't show this full example, so I just kind of repeat from my I2C guide how to read the temperature from this board. But I'll just grab this little bit of code here. So we'll say the address and the temp register. So say, you know, here's the address of the chip is 24, the temperature register is 5. And then if I want to read the value of that temperature register, I can use the read from mem function, or there's even just a read from function that I'll show here. So I can do I2C.readFrom, and I just press tab. That's the nice thing with MicroPython, you can get the auto completion. So read from is going to take, read from mem is what I want to use. And then this is going to take the device address, the register address that I want to read, the temperature register, and then how many bytes I want to read. So there are 2 bytes that I want to read from this. And so when I do that, I get some little wacky value back here. This is a byte string, and this syntax here is this /x is telling me that this is a hex value after this. So C1 is a hex value. That's the first byte. And then the second byte just happens to be the ASCII character T. So, you know, this is basically just telling me here is the value, the 16-bit value of this temperature register. And if I go through and if I run this function up here, this will pull out the temperature from it and print it out. It'll get the temperature in Celsius. But, you know, I've seen these temperature values a lot, and this looks like a good value that I got back here. So this is cool. This is I2C and kind of the basics of the usage. Now, when you're done using it, you do want to be careful and call the I2C.deinit function. So that will basically deinitialize the I2C interface. It'll prevent issues because if you initialize it and like if you soft reset the board and it's still initialized, then you'll get into a weird state where you try to initialize it again, but it's still initialized and maybe it'll work. Like I said, this is all kind of beta firmware and things are still being worked out. So be aware of that, but I will show something cool that more advanced Python users, you might want to start looking at this kind of syntax. We do support the concept of a context manager that will take care of doing this initialization and this deinitialization automatically for you. So the way you use this is with the with statement in Python, and you might see this when you deal with files. Like when you open a file, you can use the with statement to make sure that that file is always closed. So we have the same concept for the hardware interfaces like I2C in this case. So the way that you use this, you use the with statement. So we say with, and then I'm going to do this same machine.I2C function up here. Let me copy that and I'll paste this in. And then I'm going to say as I2C. So this is going to create a new block of Python code. And inside that Python code will be a variable called I2C that's going to be set to the value of this machine .I2C initializer, but it's also going to do some extra magic because it's in this with statement. It's going to automatically call this init function for me so that I can immediately start using the functions in here. So I can say like I2C.scan and call this. Now the only annoying thing with using this with statement is you see when I'm in the REPL, it's waiting for me to finish the with statement before it actually executes the code. So if you press enter 3 times, then that will actually finish the block of code and run your code inside of here. So when you're in the REPL, you probably want to use this init and dinit because then you can just interactively run your code. But if you're writing your own scripts, look at using the with statement like this because it makes it simpler. It guarantees that when this block of code is done, the dinit function is called no matter what. Like even if you reset the board, well, if you reset the board, it's not going to happen. But if you Control C and exit out of the currently executing script, it's still going to go through and make sure it deinitializes everything. So check this out. The with statement is kind of a good way to structure your code for this. Really good for scripts that you're writing. And then if you're using the REPL, you can still use this init and dinit syntax for this. So that's I2C. That's all working and looks great. I mentioned Spy, and unfortunately Spy support isn't really officially in there yet. We're working on it, so it'll be there pretty soon. So keep your eyes peeled for that. And then the last thing I'll show is NeoPixel support. So this is kind of cool. We do support NeoPixels. So I've got a strip of NeoPixels hooked up right here, and I'll connect their input to one of the digital pins on the board. So I'll connect it to, how about pin 6, we'll say. Okay, so I'll go back to the board. And to use them, it's just like using NeoPixels on the ESP8266. So there's a NeoPixel module, so I import that module, and then I create a NeoPixel object. So this is the NeoPixel class, and I want to pass in an instance of the pin, and it's pin D6, so digital pin 6 that I want to use here. And just to be sure, I'll make it an output, machine.pin.out here. And then this takes in the number of NeoPixels. So there are 8 pixels on this little strip that I have here. So I'll give it 8 pixels. And then at this point, I can just go and reference each of those 8 pixels like it's an array. So pixel 0, I can send it in a tuple of values of 3 values. So the red value, the green value, and the blue value. And these are values between 0 and 255. So this basically means full red, no green, no blue. So this is a red pixel. And then I can say, let's say the next pixel should be a full green pixel. Maybe the next one should be a full blue pixel. And then the next one, maybe we'll say is like a white pixel, like completely on in this case. And then call the write function. And you can see, check that out, red, green, blue, and then white. And it's a little bit hard to see because it's maybe blown out a little bit by the camera. So maybe if I go back and let's set these to smaller values, like let's say 50, and then let's say 50 for this, and then 50 for the blue, and then how about 50, 50, 50 for 3. So say pixel 3. So I'm just going to set these to kind of less intense values here. So I do that and then write this back out. And okay, now you can see it's red, green, blue, and white on there. So real simple, just like the ESP port. This is how you can interact with NeoPixels and light up lots of strips and cool things with this. So it's the basics of accessing hardware here. You've got digital inputs and outputs, analog inputs and outputs, things like reading the analog to digital converter, pulse width modulation to control kind of high frequency signals, to like dim an LED, even the digital to analog converter, which I didn't show here, but there's cool stuff to use with that. You can start talking to I2C devices. And then even NeoPixels we've got right here. So, there's some cool stuff that you can start to do with this port. And then I do mention the OS module. So that's the module that has all the file system commands. Most of that stuff is supported the same as other boards. The time module, we have a few things in here like how to sleep. And then we also put in this ticks function, which lets you, if you're doing like an animation loop, you probably want to know how much time elapsed between iterations of the loop. So you'll want to use these functions here. Look in the future, we'll do more projects and videos that kind of show off how to use these things. And again, like I said, a lot of this stuff could change. We're still thinking about how we want to structure our MicroPython port and some of the modules and things going forward. But this is, hopefully getting some of this info out there so people can start playing with it and trying it out. And like I said, you can play with this, you can load this firmware onto your Feather M0, and then when you're done with it, if you realize, okay, I've played with MicroPython as much as I want right now, you can load Arduino sketches back onto it. You're not going to do any damage to the board. It can run all of your old things, and then you can later come back, as we add more support to MicroPython for this. Okay, the last two things I want to show real quick are some really cool features that are sort of specific to the SAMD21 port. So we do have USB mass storage support, so this is pretty cool. If I open up my Finder here, you can see I have this MicroPython device right here that's connected, and this is cool. It is a file system that's my computer can access, and so there's a main.py file on here. Like, I can open this thing up, and let's see, do I have a good, yeah, let's just open the text editor here. So, here's my main.py file. If I want to put some code in here, I can save it here. My boot.py file is on here. There's a little readme here. If I want, I can create a file on here. Let's see. Let's go to maybe my terminal here, and we'll say, let's make a test.py file, and let's just put a function in here. We'll say, how about add? It just adds like an A and B number, and then we'll say return A plus B. So this is, just a simple little Python module, this test.py module. And if I go find that, I think that's in, let me go find this directory real fast where I put this thing. So it's in this folder, in there. There we go. So I've got my test.py file right here. So that has that add function. I'm going to copy it. I'm going to go to my MicroPython drive. I'm going to paste the file in here. And then one thing I noticed right now, you might need to reset the board. So I'm just going to press the reset button just to make sure that the file is accessible to MicroPython. And now let's open up the screen terminal again. And I'll import the OS module. And if I call the listdir function, this is going to list everything that it sees in the file system. And check this out. Here's test.py. So that's the file I copied over. And I can actually import that. So I can say import test. And I can call test.add. So like 1 + 1. And there you go. So I've just copied over my Python source code and imported it without having to use anything like Ampy or any of those tools. It's really simple and easy to do this. And this is cool. This is something that only this SAMD21 can do because it can act like a USB device, like a complex device, like a serial device and a mass storage device. The little AVR processor on an Arduino unfortunately can't do that. So you can't really do those types of things in this case. So, or at least maybe it can, but at least it can't do it as capable as the Cortex M0 on this board. So, okay, so that's cool. So USB mass storage, we're hoping that this is going to be the way that a lot of people use these boards for developing their own scripts. You can just drag and drop files over them, but you still can use tools like Ampy. That's the tool that I created that lets you use the serial connection to copy files between boards. That's still perfectly fine to use that because the serial connection is still there. So either way works for this. And I do put a big warning in here. There is a known issue if you're using the USB mass storage device. So, if you're copying files in from your Mac or your Windows machine or your Linux machine, and you're also writing in your Python code to the internal file system at the same time, there's a race condition there. And so you might corrupt the entire file system. So just be aware, try not to run code that writes to the file system while you're using the mass storage device, like while you're copying files and things between it. So, if you need to do that, you probably want to think about, what your code is doing, like just stop using USB mass storage potentially. We're thinking about maybe ways to work around this or deal with this or maybe make this less of an issue. But, just be aware there is some potential there to mess everything up. And again, this is beta firmware. There very well could be bugs that wipe out your whole file system anyways. So, back things up. Don't assume that everything is great here. Okay, the last thing, let's see. I think I've got enough time. I'll run through this really fast. So we do have support for frozen modules. I've done a whole guide on this that I link to in here. So you can freeze a module into the source code or into the firmware of your MicroPython build so that it reduces the memory usage and makes that module available to you. The NeoPixel module that I was just using is actually a frozen module that I put into the SAMD21 port. So it's a good way when you have some code like a driver that you want to use, you can freeze it into your firmware so that you don't have to load load it into RAM and take some hit there. Now there are two ways that we support frozen modules. One way is what I call an internal frozen module, and this is really similar to the ESP8266 port, where when you download the source code to this MicroPython port, there's a modules folder, and any Python files you put in there will be automatically frozen whenever you build that module. The second way that I'll show right now is what I call an external frozen module, and maybe that's a bad name, but basically it's a .mpy file. And this is a file that is Python source code that's been pre-processed into a smaller bytecode format. And then once it's in that bytecode format, it won't take up as much space as just the raw Python source code. But you can use that just like it was a .py file. So you can copy it onto the file system. You can import it from your Python script. You can use it just like any other Python script. So it's kind of handy. It's hopefully how we're thinking about using modules and drivers and things in the future. So like if you have a Feather board and you have something like maybe the Feather OLED wing, and you want to put this on your board and start using it, we're thinking of ways of how we would distribute a library for this, and distributing a .mpy file is kind of what we're thinking. You download the .mpy file, drag it onto your board using the USB mass storage, and then import it in your script and start using it and go crazy with it. It should hopefully give an easy kind of workflow for distributing different source files that are a little more efficient than just distributing the bytecode, the source code, or the Python source code for it, but maybe not as efficient as jamming it all into the firmware with the internal frozen modules. But there's a trade-off there because, like I said, this chip only has 256 kilobytes of flash memory. We're using about 190 kilobytes or so right now for our MicroPython port, and it's not super optimized, but most of that space is taken up by all of the modules and stuff and the support for MicroPython. So a lot of the modules and things that you're going to add in the future are probably going to be external ones that you have on like an external flash or SD card or something like that. Anyways, though, long story short, it's really easy to convert a .py file into a .mpy file to do this. Now, to make this work, you do have to have the whole source code set up. So go to the build firmware page, follow all of these instructions. You'll get this virtual machine set up using a tool called Vagrant. And once you have that, though, it's pretty easy. So I'm going to cancel out of this. I'm going to start up my virtual machine here. So I'm going to run this Vagrant up command. And so this is the SAMD21 MicroPython firmware virtual machine. I'm going to start it up and I'm going to connect to it. And I'll show you it has this MPY cross tool, which is a cross compiler that basically converts Python code into MicroPython bytecode. And that's all that I really need to do is just run this tool against a Python file, and then it'll give me this .mpy file that I can copy to my board and import and use. So, okay, so it's loading up my virtual machine. There we go. It's just finished loading it. And I have to give my password because it's using this NFS share so I can edit the source code. I mentioned this in the guide. There's different ways to set this up. Okay, so I'm going to SSH into my little build machine here. And in a second, okay, so now I'm in the virtual machine, which is a little Linux machine. And inside the source MicroPython and then mpy-cross directory, this is where you want to be. And if I mentioned in the guide, but you do have to make sure that this tool is built. So you just want to run the make command in here, and this will compile the tool. And so now there's this mpy cross tool in here. And so this just tells you here the options for it. And it's real simple to use this. So I'll make another Python file in this directory. So let's make a test.py file. And just to make this one different, let's add a subtract function to it. So A and B, and then we'll say return A minus B in this case. So like here's an example Python input file. To use the tool, you just want to run mpy cross against test.py, any Python file. And then by default, it should work. There should be no errors or anything. It's going to output this test.mpy file right here. Now in this case, it's a little bit bigger than the test.py file. That's because it's just a toy example. I just have one function. When you have a real script with hundreds of lines of code, it's going to be a lot smaller. Now I do need to copy this out and put it onto my MicroPython board. From inside the virtual machine, the easiest way to do that is to just copy that mpy file into the /vagrant folder. And so that's going to copy it into this synced Vagrant folder that Vagrant sets up. So I'm going to exit out of the VM, And then now that I'm out of the VM, if I look in the current directory, there's a source directory. This is where the MicroPython source code is, and that's just because I enabled this sync of the source code. I mentioned in the guide, you might not see this, but there's also this vagrant subdirectory. So if I go into there, then I can actually see, here's this test.mpy file, and I had some other files in there already, but if I look at this, you can see test.mpy, it's just modified a second ago. So that's the file. So this is, on my host machine right here. So I can just copy this onto the board's file system. So let me do that. Let's bring up our Finder here, and let's delete this test.py. So we'll move that to the trash. So hopefully that's gone from the file system. And then I'm going to go real fast and I need to go find this file. So I'll go find it over here. And yeah, here is my... Yeah, so here is the test.mpy file. So I'm going to copy this. We'll go back to the MicroPython board. We'll copy it here. I realized before I probably should cleanly disconnect the board. So I click that. So now it's ejected. Then I'll reset the board. And now let's go to our terminal and let's connect to that serial REPL again. Okay, so let's do the OS lister, os.lister. So we'll just list all the files in the file system. And hey, this is good. We see the test.mpy. So let's import test. That's good, that worked. And now I should have test.subtract. Hey, there we go. So 2 minus 1 gives you a 1. So that's cool. So that's using that external frozen module. So we did that pre-processing step where I converted the .py file into the .mpy file, copied it onto the board just using the USB mass storage, and then I'm able to import it and use it. And the nice thing is this uses a little bit less memory, in some cases a lot less memory than just importing the raw Python source code. So if you run into memory issues, maybe try converting your scripts into these external frozen modules. If you still run into memory issues, go back to the guide and look at this internal frozen module thing. You might be able to get away with that. But again, at some point, hey, this chip only has 256K of flash, 32K of RAM, and again, a lot of that RAM is going to be used by MicroPython. So you're not going to do tons of things with this, but you're going to do some cool stuff with this. Hopefully in the future, this could be kind of an Arduino-like board with similar capabilities, able to run the same kind of scripts and code and do the same kind of cool projects like build robots, build interesting IoT projects, talk to hardware, like wearables. I'd love to see some MicroPython wearables. That would be super cool to start seeing some stuff like that. And the feathers are kind of a good form factor for that. So hopefully you'll be able to start doing those Arduino type projects in a high level language like Python and MicroPython. So this is going to be pretty fun and exciting. So okay, that's it. That's all I wanted to show in this video. I think we're just about at an hour, so I'll wrap this up. If there are questions, throw them in the chat, and I'll see if I can get to them. Let's see, let me go back to the main headshot. And then I'll just kind of summarize. So again, in this video, we looked at the SAMD21 microprocessor and a brand new port of MicroPython that we've been working on for that board. And we've basically got an initial kind of beta or experimental release of it. It's not ready for complete beginners yet, but it's ready for people that have played with MicroPython and want to play with it on a new platform like the Feather M0 or the Arduino Zero. So definitely check it out, kick the tires, give us some feedback. By the way, too, I should mention, if you do run into bugs and issues, I mentioned in the guide, go to our GitHub repository. I have a link to it. Search the issues first, make sure that there's not already an existing issue for it, and then feel free to raise issues on there. We're still developing things, we're still fleshing things out, so don't be surprised if there's certain modules that aren't implemented or maybe behave slightly differently than other boards. That's kind of the fun of, we're still kind of creating this and making it as we go here for this. So let's see. Some comments in the chat. Someone was wondering, does it do floating point? Oh yeah, so Scott actually is in the chat too, and he's mentioning that, yeah, there's float emulation. So yeah, there is no floating point processor. The fancier boards like the Cortex M4, I believe, is the one that usually has, or M4F has floating point. And I think the Pi board is one of those boards that has that fancier processor. So the nice thing is, though, it still can do floating point math. It's just slower because it has to kind of do that in software. So it's it's doing that floating point math just with a lot more operations. So if you're doing float heavy stuff, it's going to be a little slower on these types of boards. But again, if you could look at something like the Pi board potentially as a faster board for that in this case. So Let's see. Someone was mentioning that the 1.85 release of MicroPython activates the .mpy files on the ESP8266. That's cool, yeah. So like the .mpys, the external frozen modules that I was mentioning, unfortunately weren't supported on the ESP8266, but maybe in the latest release they are supported. So hopefully, you know, I have a feeling at some point in the near future they're going to start supporting it. And that could hopefully be a good way that we're going to start distributing some of our code, is using that kind of thing. So. Okay, cool. I don't see any other questions, so I'll wrap this up. So thanks a lot for watching. This is Tony from Adafruit. Check out youtube.com/Adafruit. You'll see this video, all kinds of other fun project videos. I'll check out twitch.tv/Adafruit. I like to do a couple live streams a week. Only did one live stream last week. I'm kind of getting over a cold, and we're kind of racing to finish up this firmware stuff, so it took a little bit more extra time. But in the near future, I want to get back into playing with hardware and MicroPython, especially all of the feather wings. So I mentioned in the last video, we have some initial code to start supporting some of our feather wings. And now that we have our SAMD21 port, we're probably going to start playing with how we can support those and looking at how to use like the OLED and the Charlieplex and the servo driver wing. So in the next few videos, I'm hoping to explore using some of those libraries and playing with those different feather wings. And then at that point, like, you know, game on. It's ready to start building some fun projects and things with MicroPython. Like I said, I'd love to do a robot. I'd love to do some wearable stuff with MicroPython. There's a lot of cool possibilities, I think, in the near future for MicroPython. But anyways, check out twitch.tv/Adafruit. That's where I stream stuff live. And then thanks a lot for watching. You know, like, comment, subscribe. Let us know that this is useful info, especially this SAMD21 port of MicroPython. Like I said, it's experimental. It's out there in an initial release. We want to get feedback on it, see what works, what doesn't work, what people like, and you know, hopefully we'll kind of keep going with this, and you'll see a lot more fun MicroPython stuff from us in the future. So until then, it's Tony from Adafruit. Thanks for watching.